Hey, welcome to OnCallGrid Academy. This is lesson 001 PLC Fundamentals, what every maintenance technician should know before you ever touch a control panel. By the end of this one, you'll know what a PLC actually is, the major parts inside it, how it thinks in a loop called the scan cycle, and where you'll see this stuff running in the real world. Here's the thing, every plant, warehouse, and production line needs to run reliably, safely, and efficiently. That used to mean rooms full of hardwired relays. If you needed to change how something worked, you were rewiring panels by hand. PLCs, Programmable Logic Controllers, replaced all that. Same job, but now it's software instead of a wall of relays. Way easier to modify, troubleshoot, and expand. You'll find these things everywhere: conveyors, packaging lines, warehousing, manufacturing. If it moves, sorts, fills, or seals, there's probably a PLC behind it. So what is a PLC, really? Forget the technical name for a second. Think of it like this. It's the brain that watches, thinks, and reacts for a machine. It watches the real system through sensors and switches. It thinks by running the program you wrote, checking conditions against that program. And it reacts by turning things on and off, motors, valves, lights, whatever the machine needs. Physically, it's a rugged industrial computer built for exactly that job. Let's walk the hardware left to right because this order matters. First, power supply, 24 volts DC. That's what feeds the whole system. Next, the CPU, the central processing unit. This is the brain. It executes your program, does the diagnostics, and handles communications. Notice it's got a built-in Ethernet port right on it. That's how it talks to an HMI, SCADA, or other PLCs on the network. Then the input module, digital inputs. This is where your field devices, push buttons, sensors, switches, plug in. 0 means off, 1 means on. Simple as that. Right after it, the output module. Same idea, but sending signals back out to the field. 0 off, 1 on. And last, the communication module. On this one, it's RS422/485 serial H, a separate physical link used for things like drives or point-to-point serial connections. That's different from the Ethernet on the CPU. Don't mix those two up. They're two separate communication paths doing two separate jobs. Now here's something worth internalizing early before we go any further. Experienced technicians rarely blame the PLC first. When a machine stops, the PLC is usually not what actually failed. Before you ever replace one, walk it in order: sensor, wiring, the 24-volt supply, the PLC's input LEDs, the output LEDs, and only after all of that checks out does the CPU itself become a suspect. That order matters. It goes from most likely to least likely. Field devices, wiring, and power supplies fail way more often than the PLC's own logic does. Actually, pause here a second. Look back at that architecture diagram and see if you can point out the push button, the photo eye, the proximity sensor, and the limit switch. If you can name all four without peeking at the labels, you're ready to keep moving. Now here's the part that trips people up when they're new. How does the PLC actually think? It runs in a loop called the scan cycle, and it happens over and over continuously in milliseconds. Step 1, read inputs. The PLC checks every input device and stores that status in memory. Step 2, execute logic. The CPU runs your program against that input data, comparisons, timers, counters, math, whatever your logic calls for. Step 3, update outputs. Based on what the logic decided, the PLC turns outputs on or off. Step 4, repeat. It just starts over at step 1 continuously. That's it. One thing worth knowing, communication and diagnostics aren't some separate fifth step. They're happening inside this same cycle in the background. And here's why that speed actually matters out on the floor. A PLC runs through its entire scan in just a few milliseconds. So a lot of what gets called an intermittent fault isn't the PLC being slow, it's loose wiring or a flaky sensor. The PLC is almost never the bottleneck. Quick fact for you. A PLC with a fast scan time can run through its whole program hundreds, sometimes thousands of times a second. That's fast enough to catch a sensor change quicker than your eye could ever register it. VSOO2 shortcuts from here: scan, cycle steps, plus grid insight, plus did you know? Let's talk real hardware you'll actually touch. Typical inputs: push buttons, photo eyes, proximity sensors, and limit switches. These are how the outside world talks to the PLC. Typical outputs: contactors, solenoid valves, indicator lights, VFDs, variable frequency drives, and buzzers or alarms. These are how the PLC talks back to the outside world. And here's something worth keeping in mind for each one. What does it typically look like when it fails? A push button wears out at the contacts. A photo eye picks up a dirty lens or drifts out of alignment. A proximity sensor's sensing distance can drift over time. A limit switch's roller arm can just snap, and sometimes the contact itself stops working, so it's worth checking whether it's wired as normally open or normally closed before you assume the switch itself is bad. On the output side, a contactor's contacts pit, a solenoid coil burns out, a stack light bulb or LED segment dies, and a VFD trips a fault or its cooling fan gives out. Honestly, knowing the common failure for each device is half of troubleshooting it. So if an input never seems to change on, don't jump straight to blaming the PLC. Work it in order. Measure the 24 volts, check the sensor's own LED, verify wiring continuity, watch the PLC's input LED, and only then start suspecting the input itself. Same idea on the output side. If the PLC's output LED is lit, but the contactor never actually pulls in, don't replace the PLC. Check the coil voltage, look for a blown fuse, check the overload relay, look for a broken wire or a failed coil. The PLC already did its job. It energized the output. Something downstream just isn't responding. One more habit worth building now, even though we'll get into VFDs properly later: never clear a VFD fault before you've written down the fault code. The fault history usually tells you more about what actually happened than the machine's current state ever will. Let's put it together with a real example: a conveyor system. A start push button, photo eye, and limit switch send signals to the PLC inputs. The PLC continuously evaluates those inputs using its control logic. When the required conditions are satisfied, it energizes the output, controlling the VFD/contactor, which starts the conveyor motor. At the same time, it drives the stack light to indicate the machine's operating status. For the complete wiring layout, I/O addressing, and signal flow, refer to OCG-D004 conveyor control example. Let's walk that sequence in order. Operator presses start. Photo eye confirms products there. PLC starts the conveyor. Product reaches the limit switch. PLC stops the conveyor. Stack light goes green. That's not some simplified textbook version. That's exactly how thousands of real warehouse conveyors run every single day. All right, here's one to think through before I give you the answer. The motor doesn't start. The PLC's run light is on. The photo eye is on, but the output LED is off. What do you check next? Take a second on that. The answer is the program logic, not the wiring, not the output module, not yet anyway. Run light on means the PLC's scanning fine. Photo eye on means the input made it in just fine too. But the output LED being off means the PLC itself hasn't decided to energize that output yet. That points to the logic. Maybe another interlock, a timer, some second condition that hasn't been met. Not a hardware failure downstream. VSOO1 shortcuts from here. Conveyor sequence plus instructor challenge. Before we wrap up, let's cover the mistakes that eat up the most troubleshooting time. Don't assume the PLC is bad before you've actually checked your inputs. Don't ignore the status of safety devices. Always verify your outputs are actually doing what the program says they should. Watch for incorrect wiring or loose connections. More failures come from this than people expect. Check your field devices themselves before blaming the controller. And never skip lockout tagout procedure. One thing that's easy to forget mid troubleshoot: a PLC does not replace lockout tagout. Even sitting in stop mode, always isolate electrical energy before you touch any wiring. Before you replace any component, any component will run through these 5 questions. Is power available? Is the input actually reaching the PLC? Is the PLC making the right decision? Is the output energized? Is the field device itself actually working? Follow the signal, not your assumptions. One more before we move on. A conveyor won't start. Run lights on. Start button works fine. What do you check first? The CPU, the output LED, the contactor coil, motor voltage, or the overload relay? The output LED, run lights on, and the button works. So the PLC's scanning fine and got the input no problem. Fastest next check is whether that output LED is actually energizing. That tells you if the PLC is even commanding the output before you go chase the contactor, motor voltage, or overload relay downstream. Quick recap on terms. PLC is Programmable Logic Controller. CPU is Central Processing Unit. Scan cycle is that repeating loop. Read inputs, execute logic, update outputs, repeat. HMI is your human-machine interface. SCADA is supervisory control and data acquisition. VFD is variable frequency drive, and a contactor is just an electrically controlled relay used to switch power to a load. Last thing, and it matters every single time, always verify and test your I/O wiring, device operation, and program logic before you place any equipment back in service. That's lesson 001. Grab the student guide if you haven't already. It's got everything we covered here, the full knowledge check, and the glossary. Next time, we'll go deeper into wiring, sink versus source, and how to read an actual I/O circuit. See you in the next one.